All right then, sorry for the delay. Finally figured out that the camera for some reason decided to shut off, and well, cool, now we're back. So as I was saying, here we are in, as we're trying to figure out how to count solutions to this equation upstairs where we have upper bounds on these variables. So what we're trying to do right now is we're trying to figure out how to count all the solutions to the following equation, and I was setting it up before the video cut out. We are trying to find three combinations that break property 1. So namely, I'm looking at all solutions to this equation with integer solutions such that x1 is at least 2 and all the other variables are just non-negative integers. And this isn't too bad to solve. I mean, we're familiar with it. This is, we make the change of variables to get over here to the following equation, y1 plus y2 plus y3 is 1. And then all we're doing is we're just saying so y1 is now x1 minus 2, so we're changing where 0 is, and we're just solving this equation instead. And we know how to solve this. There are, let's see, there are 3 plus, I need 3 spacers, or 3 minus 1 spacers, and I choose 3. So it would appear that there are 3, 4, 5 solutions there, and 3. Is that right? No, sorry, my fault. There's one thing here. I'm trying to place one guy among these 3 spaces, and I'm choosing one place for it. That's 3, choose 3, or 3 solutions to that equation. That sounds better. Cool. So that's how we count S1. So now we count S2. Now S2 is a little more finicky. No, it's the same problem. S2 and S3 are actually counted the same way. So I'm actually solving x1 plus x2 plus x3 equals 3, so I'm making a 3 combination. And now I'm just making sure that x2 is at least 3. And then x1 and x3 have to be non-negative. I think it's pretty straightforward to see that there's only one way to do this, and that is just to make x2 equal to 3, and x1 and x3 are both equal to 0. So there's exactly one way to do this. Very similarly, S3 is counted the same way, so that there's x1 plus x2 plus x3 is 3, and x3 now is the thing that's at least 3. x1 and x2 are both non-negative. We still get that one solution. So there's one way to make this happen. All right, so now that gives us the solutions when we have, let me go ahead and zoom in a little more for you. And voila. Maybe a little further out there so I know where my boundaries are. There we are. So now we need to count the pairwise intersections. So this is S1 intersect S2 to start. Now, what we're literally trying to do here, we are trying to count these 3 combinations, but now we're trying to break not just property 1, but we're trying to break property 1 and property 2 simultaneously. So that means we need to require that we're making a 3 combination such that x1 is at least 2 and x2 is at least 3, but x3 can be any old non-negative integer. It should be easy enough to see here that if I require x1 and x2 to be at least 3, then this left-hand side, or x1 is at least 2 and x2 is at least 3, then this left-hand side has to be at least 5. And this corresponds to the change of variables where we set all the y's non-zero and set them equal to a -2. And that -2 is kind of a damper on this non-negative solutions criterion. So this is actually impossible. So that there are no ways to do this. And in fact, this set is empty. Similarly, you'll see the same restrictions on S1 intersect S3, S2 intersect S3, and also on the triple intersection S1, S2, and S3. So these are all zeros, which means after we deal with the singleton cases, everything else is gone. There's no way to make any other solutions to this equation. So then the principle of inclusion and exclusion says that the number of things I want to count, the three combinations that don't satisfy any of those three properties, is given by the 10 that I could have made in total, subtract off the singletons, so I'm satisfying one condition, add back in where I'm satisfying two conditions, and subtract out where I'm satisfying all three. And this is just 10 minus 5, which is the 5 that we expected to see, because we listed out all 5 of those three combinations. All right, so it might be more useful now to go through an example where we have fewer zero counts involved. So let me outline another example here, and that might be a little too close. There we go. So now I would like to count the number of 10 combinations of the multiset S given by 3 A's, 6 B's, 4 C's, and 8 D's. Okay, so we are going to set this up as before. Create S star to be the unlimited supply multiset. All right, and then we count the ways to create 10 combinations of that. So the universe is going to be all 10 combinations. 10 combinations of S star, and we count those as 10 things I want to put in my subset, and then I have 4 types, subtract 1 to put in the dividers, and I have 10, so that is 13, choose 10. All right, so now let's list the sets. The sets that we want to count, so list the sets as SI. These are solutions. They contain all the solutions to the following equations, where I have x1 plus x2 plus x3 plus x4 is equal to 10, right? I'm making my 10 combinations, and that's coming from the multiset S star. And I want to make sure that xi is strictly greater than its repetition number in S. So repetition number of xi in S. And xi I'm referring to loosely as either an A, B, C, or D. And I would also require that all these different variables, so I'll call them xk's, are non-negative. Cool. So I need to solve these equations. All right, so let's count x1 or S1. S1, these are the solutions to x1 plus x2 plus x3 plus x4 equals 10, such that x1, if I bring the list back down, notice that A corresponds to the x1, so x1 corresponds to the number of A's I'm going to put in the set. The repetition number on A in S is 3, so I need to make sure that I break that restriction and make sure that I include more than more A's than are available to me. And then x2, 3, that is a 3, and then 4 are all non-negative. Cool. And we know how to solve this. This is equivalent to the system of y's adding up to 6, where all the y's are non-zero. This gives me 6 plus, I have 4 different types, so I need 3 separators, and choose 6 places. This is 9, choose 6. All right, so very similarly, we can count S2 and S3. So S2 is going to be 6, choose 3. I'm also going to need an S4, right? I'm going to need S3 to be 8, choose 3. And S4 is counted as 4, choose 1. Cool. Now we go for our pairwise intersections. To count S1 intersect S2, I'm now solving x1 plus x2 plus x3 plus x4 equals 10. I'm making my 10 combination, and I'm breaking both property 1 and property 2. So I need to make sure that x1 is bigger than the repetition number of A in S, and x2 is bigger than the repetition number of B in S. And I need x3 and x4 just to be non-negative. This corresponds to the system of y's that actually sum up to -1. So that means that there, again, are no solutions. So impossible to do this. And we're actually going to see a similar case for most of the other pairwise intersections. So similar for S1 intersect S4. In fact, any of them where the repetition numbers have to add up to something greater than 10. So this will be S2 intersect S3 as well, S2 intersect S4, and S3 intersect S4. And these are all 0. But wait a minute, there's 1, 2, 3, 4. I've only counted 5 of my pairwise intersections. The case is slightly different for S1 intersect S3, because all I have to do in that case, the numbers that I have to use, I have to make sure that x1 is at least 4 and x3 is at least 5. That's not greater than 10, so that means that there are actually solutions sitting in S1 intersect S3, and I can count them as 4, choose 1. I'll leave it to you to show that. But I do want to remark that beyond these pairs, there are empty intersections. Apart from the pairs, all other intersections are empty. Intersections are empty. So that means that after I've counted all my pairwise intersections, everything else is 0, so principle of inclusion and exclusion basically stops after that. So then all that's left over now is the set S. I want to count the total number of things in S. That came from 13 choose 10 possible 10 combinations minus the singleton combinations that break the rule, or that break the restrictions. And then I tack back on the pairwise intersections. There are 6 of them. Only one of them actually counts toward our final goal. And then I count my triple intersections. All of them are empty, so they contribute 0. And then my quadruple intersection is added back in, but again, that one is empty. So all I'm left with are 126 10 combinations in S. And that'll about do it for section 6.2. Now, here's the plan for the next few days. I will not be back in town in time for office hours on Monday or Tuesday this week. So today or tomorrow. Oh no! Video. Oh, we don't need the video, but I want the video. Okay, whitewash screen again. So office hours will start back up on Wednesday. Wednesday and Friday are after class for an hour or 2. And then there are the office hours on Thursday morning from 10 to 12. Your midterm will be next Monday, all right? I am not planning on having a review session for it. I may or may not include practice problems. Your homework, I feel, should be sufficient study for you to be prepared for the exam. Let's see. That exam will only go up through what we're covering on Wednesday, which brings me to Wednesday. We are adding on an extra section. I know I only included up through section 6.3 in the syllabus, but 6.4 is actually new to me, and it actually looks really interesting. It's something that's very, very applicable and gives you one more piece of context in which you can apply the principle of inclusion and exclusion. So I would like to add that to the syllabus. We may or may not test you on 6.4, but it is an interesting application, and I'm not saying whether or not that's it is testable, but unlikely that it will show up on the exam. So I'll say that much. If it does show up, it'll be some sort of small question, not worth too many points. But here's what we're going to do afterwards. So after we're done with derangements and the forbidden positions sections, 6.3 and 6.4, we're going to move straight into our next unit. So we're going to start graph theory on Friday. That's chapter 11. And if you would like to get a head start on it, which I highly recommend because there are a lot of new terms, a lot of new concepts that we need to hash out on Friday, and it will make it all the easier for you in lecture if you at least read section 11.1 before Friday's lecture. It will help immensely, I promise. So that's all that we're going to do for today. I'll be back Tuesday evening. If you need to get in touch with me for in some way or another, my email is open. Just make sure your comments are brief. I don't know how much time I'll have to devote to any responses. So if you need to get in touch with me about something, any particulars, something that needs a kind of a longer explanation, I will be back on Wednesday, and we can talk then. If you have registered with the SDC, you need to email me, or I will email you. I will email you. We'll figure this out online through email. So, other than that, I think that's it. I will be back on Wednesday, and I'll see you guys in class. Take care.